Imagine a population in which every individual lives for one generation, produces a random number of children, and then disappears. Some family lines grow rapidly, some remain small, others end immediately. A branching process models this random population growth. Its central question is simple. What is the probability that the population eventually becomes extinct? Let xi sub n represent the number of individuals alive in generation n. Each individual independently produces a random number of offspring. After reproduction, the current generation disappears. So the next generation consists entirely of the children produced by the present generation. Suppose the current population contains I individuals. Each one produces a random number of offspring. The next generation is therefore the sum of those I offspring counts. The probability of moving from population I to population J is the probability that those offspring counts add up to J. Notice that we only need the current population size. The earlier history no longer matters. That is exactly the Markov property. The state space is 0, 1, 2, 3, and so on. State 0 represents extinction. Once the population reaches 0, no individuals remain to reproduce. So every later generation also has size 0. State 0 is therefore absorbing. First, suppose each individual has a binomial number of offspring. Each parent has capital N possible offspring opportunities, and each succeeds with probability P. For one individual, the offspring count follows a binomial distribution with parameters capital N and P. With I current individuals, there are capital N times I independent offspring opportunities. Therefore, the next population follows a binomial distribution with parameters capital N times I and P. The probability of producing exactly J offspring is capital N I choose J times P to the J times 1 minus P to the power capital N I minus J. If J exceeds capital N I, the probability is 0. Each parent can produce at most capital N offspring. Now suppose each individual has a Poisson number of offspring with mean lambda. The sum of I independent Poisson variables is again Poisson with mean I lambda. So if the current population is I, the next population follows a Poisson distribution with mean I lambda. The expected next population is I lambda. That makes lambda the average number of offspring produced by one individual. The value of lambda determines the broad population regime. When lambda is less than 1, the population shrinks on average. This is the subcritical case. When lambda equals 1, the process is critical. When lambda is greater than 1, the population grows on average. This is the supercritical case. But average growth does not guarantee survival. A population can still disappear during its first few generations. Let phi of I be the probability that the population eventually becomes extinct when it begins with I individuals. If the process starts at 0, extinction has already occurred, so phi of 0 equals 1. For positive I, phi of I measures the chance that the population reaches 0 at some future generation. To calculate extinction probability, condition on the size of the next generation. Starting from I individuals, the next population may contain 0, 1, 2, or any other number j. If the next population is j, the remaining extinction probability is phi of j. Therefore, phi of I is the weighted average of phi of j over every possible next generation size. This gives the extinction equation. Phi of I equals the sum of phi of j times the transition probability from I to j. Suppose the extinction probability of one family line is R. If we begin with I individuals, each creates an independent family line. The full population becomes extinct only if all I lines become extinct. The probability of that is R multiplied by itself I times. Therefore, phi of I equals R to the power I. The corresponding survival probability is 1 minus R to the I. For Poisson offspring, substitute phi of j equals R to the j into the extinction equation. The resulting sum is an exponential power series. After simplifying, we obtain R to the I equals e to the power I lambda times R minus 1. Taking the ith root gives the fixed point equation R equals e to the power lambda times R minus 1. Equivalently, R equals e to the minus lambda times 1 minus R. The extinction probability for one initial individual must satisfy this equation. The equation always has the solution R equals 1. When lambda is at most 1, extinction occurs with probability 1. When lambda is greater than 1, there is another solution, f, between 0 and 1. The correct extinction probability is the smaller fixed point. Starting with k individuals, extinction probability becomes f to the k. Survival probability becomes 1 minus f to the k. Even when lambda is greater than 1, extinction remains possible. The process grows on average, but each generation is random. The first few individuals may produce too few children. The population may reach 0 before its average growth rate has time to dominate. So expected growth is not the same as guaranteed survival. The offspring generating function packages the entire offspring distribution into one mathematical object. It is defined as the sum of pk times x to the k. For Poisson offspring, this becomes e to the power lambda times x minus 1. The extinction equation is simply R equals f of R. So extinction probabilities are fixed points of the offspring generating function. F of 0 is the probability of extinction by generation 1. F of 0 is the probability of extinction by generation 2. Applying f repeatedly n times gives the probability that the population is extinct by generation n. This is repeated function composition. It is not the ordinary power f of x raised to n. Because 0 is absorbing, extinction by generation n implies extinction at every later generation. So the extinction by generation events form an increasing sequence. Their probabilities converge to the probability of eventual extinction. Therefore, phi of 1 equals the limit of the repeated compositions of f starting from 0. The sequence moves upward toward the smallest fixed point. When lambda is greater than 1, it converges to f rather than to 1. Consider the special case where each individual can produce only 0 or 1 child. The population can never increase. The generating function is q plus px. Its fixed point equation gives R equals 1. So extinction is certain for every finite starting population. Each family line may continue for many generations, but it eventually ends with probability 1. Take lambda equal to 2. The fixed point equation becomes R equals e to the power 2 times R minus 1. The smaller solution is approximately 0.203. Starting from one individual, extinction probability is about 20.3%. Starting from 3 independent individuals, extinction probability becomes f cubed, which is less than 1%. A larger starting population greatly improves survival prospects, although survival is still not logically guaranteed. A branching process models a population in which every individual independently produces a random number of offspring. The process is Markov because the next generation depends only on the current population. State 0 is absorbing and represents extinction. The generating function turns the extinction problem into a fixed-point equation. When the average number of offspring is at most 1, extinction is certain. When the average exceeds 1, survival becomes possible, but extinction may still occur. The central lesson is, growth on average is not guaranteed survival.